Let's work an example from the text. This is example 1 on page 260, where we approximate the area under the curve f of x equals x squared. So I've drawn a portion of the parabola here on the interval from 1 to 3, and let's use 4 subintervals. In other words, let's compute r sub 4 using the book's notation. Now the curve continues, but what we're interested in doing is we're interested in computing the area under the curve over the interval from 1 to 3. So this area under the curve here, and I won't shade it because we're going to have to draw in that region. If we're going to use 4 subintervals, well, right now the 1 and the 2 and the 3 partition it into 2, so we just need to draw another tick mark. Again, using the book's notation, this 1 is A, that's our left-hand endpoint. In the reading, we're referring to an interval from A to B. So x naught is A is 1 here. x4 is B, and that's 3 here. And then what would x1 be? That's this guy right here. And x2 is 2. And here's x3. And so we just need to figure out x1 and x3. We need to figure this out in this example. And so in this example, what we do is we take the length of the entire interval and divide by the number of subintervals, which is 4. And that's going to give us what we're going to call delta x, the length of the nth subinterval. And in general, what we'll do is we'll take the length of the entire subinterval, b minus a, divide by the number of subintervals we want. We'll call that capital N. That's going to be our number of subintervals. And that will be delta x. And we're just going to say delta x because we're going to have even width subintervals. There's a development of a Riemann sum where you can have varied width subintervals, but we're going to just discuss even width subintervals. So that's our length of each subinterval. So if we were to write out, and I want to write it out so we can see it, x0, the first left-hand endpoint is 1. x1 is 1 plus that delta x, that little bit that we're adding. And you can compute that. It's just 1/2, 2 over 4, which is 1/2. So that's 1 plus 1/2, 1.5, or 3/2. I think I'm going to keep it in fraction form, 3/2. And that's easy. That would have been easy enough for us to see, but what we're trying to do is we're trying to develop a general process that works for us every time to be able to write out what these right or left-hand endpoints are. You can think of x1 as a right or a left-hand endpoint in this situation. x2 is going to be 1 plus a couple of delta x's. There's a delta x, there's another delta x. So 1 plus a couple of delta x's. That's 1 plus 2 1/2, which is 2, and we knew that already. x2 is 2. x3 is 1 plus 3 delta x's. So 1 plus 3 times 1/2. This is 3/2 plus 2/2, that's 5/2. And x4, for us, capital N is equal to 4, is 1 plus 4 delta x's. That's to use right-hand endpoints, right? So that's 1 plus 4 times the length of our little subintervals. Remember, that's delta x. This is the number of them that we add to get to that last endpoint. Here's our last delta x that we're adding. And that's going to give us 2 plus 1, which is 3. Again, we knew that, but we're trying to figure out how to do this in general. All right, so now we've got all our endpoints. Let's represent those rectangles. I'm going to plot here this point that's at 1 1/2 or 3/2, and I'm going to draw a rectangle to approximate that area. Come to the next right-hand endpoint, draw a rectangle to capture some area. The next right-hand endpoint, draw a rectangle to capture that area, and so on. So now I've got 4 rectangles to give an estimate of this area. You can see that it's an overestimate because I'm counting area that's not actually under the curve. That's because this function is increasing on the interval from 1 to 3. Now, how do I figure out, how do I sum up those areas? Well, all of them have the same width. They're all delta x. So the sum of the areas is going to be delta x, which for us is 1/2, times the height of the rectangle. Okay, well, how tall is this rectangle? The thing you should notice about this rectangle is that it sits on the curve. So while the x-coordinate is 1.5, or is 3/2, how would we figure out what the second coordinate is? Well, remember that these points on this curve are points of the form x, comma, f of x. So we just need to figure out what f of 3/2 is. So that's the first height of the rectangle. Here's the width. That's the height of the first rectangle. So if I were to call this area 1, here's the area 1 expression. It's 1/2 wide and however tall that is. The next one is also 1/2 wide, and it's f of, let's see, this height, 2. Plus the next one is this point, 1/2 f of 5/2, and then the last one is 1/2 f of 3. We sum all those areas up to get the total approximated area under the rectangle, or under the curve. And you can consult your text, example 1, when you add all these areas up. And how do we apply this function f? When you add all these areas up, our approximate area is 1/2. And what is the function f? Well, f is the squaring function. F of x is equal to x squared. So we do 1/2 times 3/2 squared plus 1/2 times 2 squared plus 1/2 times 5/2 squared. And so all we're doing in this next step is we're actually applying what the function f does. And depending on what your function is, it will be different each time. We add all that up, and what we get is 10.75. You can just add all that up on your calculator, and you get an approximation of 10.75. This is the approximate area under the curve, and it's an over estimate. Whoops, I'm off screen. There we go. This is an approximate area under f of x equals x squared on the interval from 1 to 3.